All right, let's see if this works. All right, so this is the first lecture for you, Rye Guy. So let's just talk a bit about how the periodic table looks. Well, for one thing, let's actually just start here. What is matter? Well, I'm not gonna give a whole stupid definition. I mean, they try to give it a definition that's kind of like, let's see, the one that they made me write, weight and volume. But that does not, that's pretty much density. And that differs on each planet, just because of the whole gravitational pull. What matter is just what is. It's what makes everything. That's all it is. There's no way to quantify matter in a way that's relative to anything. I mean, we try to consider mass as being, I don't know, some form that you can measure and it's same everywhere, but it's not the same everywhere. So matter, the only thing that I just need to write down is matter. I mean, just everything. It's a lot easier to do it this way rather. I mean, your teachers later on will give you a different definition, but this is the definition I'll accept just because it doesn't really make any sense. I mean, if you have a ball that's 5 grams, then it weighs less on the moon. It doesn't matter if it's 5 grams on Earth because we measure it based off of what's on Earth. I mean, you could find the mass density, but that goes later on. So mass is quantifiable matter. And quantifiable, let's see, this is how you spell it, quantifiable, okay? All right, so let's keep going. So we have this word quantifiable, and I'm probably going to use this a bit. So let's just think of quality and quantity. Quantity is how much, quality is what does it look like. You know, like you can't really describe the color purple by a number other than just one, the amount of colors there are. But you can describe the color as just being purple. You get what I'm saying? So now let's keep going. Another thing I could write down, since we're on the topic of mass and matter, we can relate density. And density is the amount of mass over volume. And actually, this is more closely to what matter is, like definitively. I don't know. But it's mass per volume, and the thing is that the reason why it's so much better to describe mass in terms of this is because, well, everything is contained into one substance, right? It's just one object. So here's your object, and let's say we have this size, then if we have more mass, then it has more density. So if, like, let's say you have a ball of iron compared to a ball of aluminum. Now, if you lift up that ball of iron, it's gonna be a lot heavier. I mean, if you have a ball of uranium, that's a lot. That's actually a lot. And plus you probably get radioactive poisoning and die of pooping yourself. But let's continue on. What is a substance? Well, substance is just what describes a compound. Here, what does that mean? So let's say that we're trying to describe a water bottle compared to a Coke, or just a Coke can. So what composes the water bottle? Well, it's composed of plastic, and the Coke is composed of aluminum. Now we know that a water bottle does not shine. It doesn't have any sort of properties that you can see right through it, and that's about everything. Coke can shines. It's a lot harder than the water bottle, And if you were to heat it up, it'd probably work out very well. So a substance is this this type of matter that you can describe with some sort of composition. What is it composed of? And it has certain properties that go along with it. So whenever I say, oh, let's use the substance sodium hydroxide, the first things that you can think of is it's a strong base. Put your hand into it and won't feel too well, that sort of thing. And a mixture is just combining certain substances. Like if you add ammonium and then, I don't know, put OH at the end. And since these cancel out, it becomes a neutral atom. So then that's what a mixture is. That's all you need to know. I mean, I won't go too in depth into that because as you go through chemistry, you're going to have to deal with a lot of reactions and you'll be able to come up with your own definition of what a mixture is to you. Because I don't care how other people define it, it depends on how you can see it. But this is something that you should start looking at. It's homogeneous and heterogeneous. Okay. Here, let me just finish writing this down. Okay, so homo, same. Hetero, different. I wrote hetero. Diff. There you go. So what does this have to do with it? Well, we're dealing with mixtures over here. So I'll just put a little bracket over it. Mixture. So you have heterogeneous mixtures and you have heterogeneous mixtures. So homogeneous mixtures, let's say you've probably put, I don't know, sugar into coffee or something, right? And you know that it dissolves completely. Well, have you ever put oil into water? You notice how it just floats to the bottom and kind of separates from each other? Well, homogeneous means that it becomes, it looks like one mixture. So it's same throughout mixture. And heterogeneous is the opposite. It is different throughout the mixture. It does not actually mix well. That's how you can think of it. And you're gonna see a lot of this, and you're gonna actually run into it with solubility when different ions start connecting to each other, and I don't know, you end up with iron hydroxide and things called precipitates. And precipitate means that there's going to be some solid that grows in a certain mixture, which is going to be heterogeneous. So knowing those terms would actually help you out. But let's get past that. Let's actually just talk about what an element is. Well, elements, they're composed of certain properties. Here. This is going to be the biggest tip. Any element is going to have a certain number of protons. I mean, it could lose an electron, it could gain an electron, it does not matter, but it's always going to have the same amount of protons. Okay? And since it has the same amount of protons, it's going to differ from each element. That's why we have 1 through 119 or something. So let's think about H, or hydrogen. So it has an atomic number of 1. We'll label that as Z. Z equals 1. And what can we apply from what I just said? Well, the amount of protons in a hydrogen atom is going to be 1. We'll put P equals 1, P proton. And this has a mass of 1.008. And here's the thing, let's label this as A. If you have an atomic mass equal to some number, I don't know, it's always going to be equal to P plus N, protons plus neutrons. It's always going to equal that. So if you're given a certain atomic mass, as we've got here, then it's going to be 1.008 minus 1 equals the number of neutrons. And since it's close to 0, we can basically assume that there are 0 neutrons. So n equals 0. And here's actually something cool about hydrogen. It does as it pleases. So it can act as a positive charge and a negative charge. So it can it can treat itself like a metal, but it can also treat itself as a halogen. It's kind of goofy. That's actually why they kind of separate them in the periodic table, because it's got this property that's like completely different from the others. And you notice that like it's pretty much a special case of what Niels Bohr, he worked on quantum mechanics, what he was working on. And what he didn't anticipate is that hydrogen was special. It was completely different from the other elements, that he couldn't use his model to predict the activity of other atoms, but we'll get to that later. So it can act as a donor. That's what we call it, a donor, when it donates a proton, and an acceptor. Why did I write donor again? So it just does as it pleases. But let's see. Trying to remember what I'm talking about. Here, let me erase this real quick. I already got through hydrogen, so let's begin talking about something different. Why is this taking so long? How do I clear? Oh, clear all drawings. Okay, that's good to know. Ooh, they have. How do I draw? There we go. All right. Now we already discussed elements and how we can find a number of protons. So before we get off of how we find all of the numbers of protons, neutrons, let's discuss a bit about electrons, because electrons, they kind of differ from time to time. And even neutrons differ from time to time, but I'll get to that soon. But with electrons, it really depends on what charge they have. Because you can't assume that, like with hydrogen, which is another part of it, is that they have one proton, one electron. And that's why they act so goofily. It's the only one that does that, because it has no neutrons and it does that. But with the other atoms, when you get further out, you notice that they have a +1, +2, +3, +4 charge. And then it goes to -3, -2, -1 charge. And that's because of the amount of electrons. So if you have one less electron, you actually get more positive. So -1 electrons, it's going to be a +1 charge. And yeah, you can go ahead and be like, oh, +1 electrons, -1 charge. And you're going to notice a little bit of a pattern in the periodic table as you go along. And it's not too complicated once we get into it. It's just it's going to need a little bit of work. but we have compounds now. That's what I'll begin talking about. And compound is pretty much the same as a mixture, other than that the compound exists naturally. I mean, example H2O, that I'm pretty sure that exists. Let's see. Oxygen gas, that exists diatomically. That just means two atoms in one compound. And we could just keep going on from there, but let's continue on. So we have 4 different types of properties. And that's going to be a physical property. Let's see, physical, chemical. Let's see if I could draw my finger. Extensive. Intrinsic. Oh wait, not intrinsic, intensive. And a little thing to note about physical and chemical processes is most of the time with chemical processes, if you burn it, it'll change compounds. If you see a different color, it change compounds. But if it turned from gas to liquid, it's a physical one. It doesn't change the composition of the atom or whatever you're dealing with, the molecule. It just changes what is happening to it. So like if you put salt into a bottle of water, it spreads out, but it still stays salt. It just ionizes. That's what we call it. And for extensive properties, this just is, you don't really need to know extensive and intensive properties because you normally do this when you're in the middle of labs, like all the time. You'll get it down pretty quickly. But extensive is just how much matter is being used. What is the mass? What is the density? That's all it's asking. Intensive, it doesn't depend on any of that. So it's just what is it naturally? So we can put assign like a color to something, and that'll be an intensive property. All right, let's keep going. Now, I'm not gonna lie to you. When it comes to atoms, they'll say that it's the basic unit of an element, but that isn't really the case. It's composed of all sorts of different things, quarks, quaternions. You'll deal with all that, neutrinos, neutrons, protons, electrons. I mean, that literally right there, it contradicts what they're trying to teach you. And it doesn't make any sense why they try to teach it as a basic unit of an element. The basic unit of an element is composed of multiple things. So we have atomic particles and we have subatomic particles. Atomic particles, it's just a part of like molecules, and you probably won't deal with atoms too much most of the time. I mean, at some point we'll have to do it, but we're dealing with more like chemicals and stuff, and you'll be dealing with that a lot more. But let's keep moving. I don't want to stray too long with that. So let's just talk about the cathode ray tube. So this is actually how they proved electric or negative and positive charges. They connected these 2 gold foils, and they were able to send electrons straight through this tube into like a little ball. So it was just sent through this tube, and it was just traveling through. I believe they only used and they didn't use light. What did they use again? Crap, I can't remember what it was called. Well, basically, they sent all these electrons through this tube aiming over there. And for one thing, they showed that light was just coming out of this tube. And as they were switching which one got each charge, they found that as they were going through, it would either go this way, and if there was attraction, then it was going this way for the gold foils. It was attracting, and of course, negative would push it away since they're both negative and negative charged, and they changed this one to positive, and that's how they proved that there were positive and negative charges. Now here's I don't really like giving values of these things when it's a lot more fun to just do it. So for electrons, when you're dealing with charges, they're in units of this thing called a coulomb. And the charges of electrons are equal to negative 1.6 times 10 to the negative 19th. And I don't know if you knew this, but 10 to the negative 19th is a very small number. Think of it as 1 over 10 to the 19th. Very, very, very small. And of course, what you should know is, you know that protons and electrons, if they attract, they cancel out. They're completely attracted. They don't leave any residue or any charges left over. So what should that tell you? Well, what that should tell you is that the charge of a proton is equal to the charge of an electron. But opposite. Don't forget that. So this one's going to be positive. We'll just call it, I don't know, QE, since that's what you're going to be using. So this is just charge of electron, that QE. So positive QE right there. And neutrons, well, it's literally in the word, it's neutral. So it has 0 charge. I don't think I need to write that down. But the masses of the proton, I don't think you need to know this, but the mass is just 1.7 times 10 to the negative 24th. And of course it's gonna be that small. I mean, it's subatomic. I mean, you can't even see the atoms connecting your desk. And it's not the same thing with the masses of protons and electrons. They are not equal. They only deal in charges that are equal. But let's talk a bit about how we used to think electrons used to work. So there's this thing called a plum pudding model, where you'd have your nucleus right here. Well, not nucleus. At this time, it was just a bunch of electrons. And what they thought was that electrons were distributed as if it was plum pudding. That's what they called it, because Germans are weird. But what disproved that was this thing called the gold foil experiment. I mean, it's weird that they called this one gold foil, and they were also using gold foil for the cathode ray tube experiment from before. But this one proved the existence of a nucleus. And since that existed, there was no way that it could exist this way, distributed equally, since there was already something in place of that center part right there. And of course, this actually proved like alpha rays, beta rays, gamma rays, and it was a pretty big deal, and I'm surprised he didn't get a Nobel for that, but they discovered this nucleus, and it was completely compact. Like it contained the protons, the neutrons, and they were all just tied together. But these electrons, it's kind of weird because they're anywhere. They're literally anywhere in this little cloud around the nucleus. There's so much space around a nucleus where electrons could be that scientists have proven that we are 99.9999% empty space in all atoms. And it's just composed of electrons that, if you believe it or not, this is a proof in quantum mechanics that electrons, if you don't view them, they're basically going to be anywhere. But if you view them, they stand still, but you can't get how fast they were moving before. It's really goofy. It's really, and we won't really need to go into that. But let's keep moving. So you may need the mass of a neutron. I'll give you that one. Because sometimes you'll get to deal with neutrons moving at high speeds. And it'll be a pretty fun problem. I mean, actually, I'm not sure if you'll get one like that. But it's the same mass as a proton. And another thing you should note is this term isotope. And isotopes, so we discussed that atomic mass equals protons and neutrons. But what about an element that exists as a different atomic mass, meaning that there's a different number of neutrons? Because the proton number never changes because the atomic number, but our atomic mass can change. And that's what we call an isotope, when N does not equal the original atomic mass. Now, the way to solve this, nasty. The way to solve this is taking the average, or taking the sum. So what this means right here, it just means sum, and normally you have this to some amount of terms. So like we have I'm trying to remember what equation I wrote. I was the only one that like wrote this in my class. PIMI. And it's not a hard equation. So what it means is that it's just P1 M1 plus P2 M2 plus, and we could just write dot 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 as just following that pattern, and then plus PN MN. That's all it means. And this is a pretty good formula that you can use. But these percentages, or these P's, mean percentages corresponding to each mass. Okay, so P percentage M mass. Just get that down into this equation. You should probably define your terms down here. P percent and then M mass. Normally you should do that for all your equations, so get into the habit of doing that. But let's keep moving on. Let's draw out a periodic table. So we have our hydrogen, and we have our alkali metals, our alkali earth metals, and then you have your transitional metals. Let's see. Okay, so first thing to note, this is hydrogen, and I'm not sure if your future teacher is going to deal with this, but hydrogen is not really assignable to any group. It acts both as a metal and a non-metal. So you can decide on what you want to call it. It doesn't really matter. You can call it a thing for all I care. But this is an alkali earth metal. This is how you spell it. ALKALI metal. I did I say alkali earth metal or alkali metal? I think I said alkali metal. So this is alkali metal. This is alkali earth metal. Also known as alkaline metals, but we don't need to learn that term. It's a lot easier to name it these just because you'd be able to know where they're going to be. So if I say where are the alkali metals, you can describe it using this thing called a group. And groups they go down vertically, and they're going to be these sections of the periodic table that I'll discuss in a bit because groups kind of change when it hits transitional metals. So most of the time you're going to be dealing with non-metals and alkali metals. But we have alkaline earth metals. Right here are transitional metals. And I'll explain why they're called that in a second. But we have transitional metals. We have metalloids. Halogens. Oh wait, I pointed at the wrong one. So right here, halogens. And right up here, they're just called nonmetals. And we can also label noble gases right here. I don't, we maybe discuss this a bit in the gas section, but most of the time you're not really using them just because they don't react with anything. They don't have any charges. They're completely neutral. They can exist monoatomically, which just means one atom in itself. And nonmetals, they exist diatomically, which means two atoms as itself, and that's how they exist as gases. And noble gases they don't attract to anything, only in special cases such as like xenon and fluorine. But that's pretty much it. And that's just because of the amount of electrons and the electronegativity of fluorine, but I'll go into that later. And right here, that's just goofy. We won't be touching that. Nasty. Okay, so let's start with transitional metals. Why are they called transitional metals? Well, transitional metals are called that because they can do whatever they want. Just like hydrogen and alkali metals, which this is kind of like the adult version of them because they can attract to any negative charge thing. Because they can just donate protons whenever they want, or they can just give off charges, and the other compound or substance just accepts it, and it can have as many electrons as it wants. I mean, within natural boundaries, but if you have like a compound with a +3 charge and it wants to, or a -3 charge and it wants to attract to like copper, copper can literally have another electron just to match it. Like it's as if it's having like a measuring contest with their penises. Like that's all I can really say about that. So it's kind of fun. But actually, before we go further, let's talk about our bit of terminology that you will be needing. So if you're looking horizontally or left to right, this is what we call a period on the periodic table. And if you're looking vertically, this is what we call a group. Okay? Write this down and memorize it. Memorize it. Plant it into your head. Because if I say what looking group 7 and you don't know, or group 7A and you don't know what I'm talking about, I'll kill you. But anyway, so the A groups match up to 1, 2, and they don't include transitional metals. They'll be called a B group, and it's kind of explanatory why, because they act goofy. But you go 1, 2, skip over transitional metals, and then it's 3, 4, 5, 6, and there should be a 7. So you have 7 groups, and you have your halogens, and you also have like pnictogens and chalcogens, but we don't need to call them that. I mean, maybe you'll run into a test question in the future, but we can just leave it at this. So let's talk a bit about metals. So what can we use to describe metals? Well, metals are very good at conducting heat. They are good at conducting electricity. You should write this down, every word. Good at conducting heat, good at conducting electricity. I don't know, they're shiny. I mean, most of them are. What else do I want to say about them? I'm trying to think of what else. Sometimes they're hard. There's a good counterexample to that, which is going to be that mercury exists as a liquid metal. I mean, it's completely poisonous, but it's still a metal, or it's a completely poisonous liquid. But it's like the only one that acts like a liquid. And then we have nonmetals, which is a poor conductor of heat and electricity, but that does not mean that it can't do it. It's just that if you were to put a non-metal like carbon uh, into like a wall socket, it won't deal with it well. I mean, if you put your finger into a wall socket, it'll definitely do the trick, but you don't really use that. And metalloids, which are like alkali metals, alkali earth metals, they're kind of in between. They aren't good or bad conductors of this stuff. Okay? Let's see. And for one thing, we have this thing called an ion. And this is the charge of a certain atom. Or the net charge, I should say. So ion, net charge of an atom. What does this mean? Well, really we can nail it down to how many protons and how many electrons should they have. So if you have hydrogen, you can have 1 proton and 1 electron. If it's positively charged, then there's no electron. If it's negatively charged, it's going to be a removal or an addition of an electron. What else was I gonna say? I was trying to go off on something. Oh yeah. So here's a little trick on ions. So it goes +1. This is going in groups. So keep reading along. There will be 7 of these charges I'm going to write down. Make sure you get down this trick. It's going to help you a lot. And I mean a lot. So you have +1, +2, +3. plus 4, and then we kind of go reverse. Minus 3, minus 2, minus 1, and 0 charge, and 0 assigns to noble gases. Remember that trick. And I don't know if you can read that, but please remember it. It'll save your life. Now, let's go to molecular formulas. So molecular formulas, let's say you have some molecule. This is just an example. I'll use, or this is just a general formula. I'll use a different thing. But let's say we have some compound that's AN, BN, all the way to ZN. All right, we go through the entire alphabet. So now, this is what we call our molecular formula. It's not going to be an empirical formula. It's just whatever it needs to be. And that's kind of a goofy way to explain it. It's just what the compound is at the moment. Because if you go down to its simplest form of it, like let's do C6H12O6. This is sugar or sucrose. Now, this is an example of a molecular formula. It's in a certain form that can actually be CnH2n and ON. This is because I divided all of the numbers in C6H12O6 by 6. And then I just plugged in just some random letter. And don't think of this as too hard, because when I put letters in, all I mean is that you can plug in any number into it. That's all I mean by it. Oh, I hate it. Oh. By each formula, such as like C6H12O6, when it's kind of like that, it's going to be called an allotrope. So like an example of an allotrope is like O2 and O3. So its original form is ON. Our base form, which for this one would also be CH2O. These both are called empirical formulas. EMPIRICAL. And that's going to be everything I want to talk about. Try to leave your questions in the Google Classroom, but otherwise I shall see you in the Discord. Goodbye, babe.